class, if you would take out your homework and then get started on your warm-up. The warm-up is on the board, and the warm-up is a review of some of the material we've worked on this unit. Number one, ask you to graph any function where the domain is from negative infinity to 2, union with 4 to infinity. The range is a set that contains the element negative 3, union with negative 1 to infinity. Then on number 2, I have graphed what I tried to make an absolute value function. It's pretty close, it's slightly off, but it's pretty close. I need you to give me the domain and the range, the zeros and the intercepts, and we're going to estimate a little bit because they're slightly off. Give me any extrema, intervals where the function is increasing, decreasing, or where it's constant, and then to give me the end behavior. And then after that, I'd like you to, in number 3, give a transformation for that function that would create a function with even symmetry. So the function is slightly off, so you're going to have to use your imagination just a little bit. But what transformation would need to occur to create a function with even symmetry? Take a few minutes and work on that. And if you would hit pause on the video, and when the students have completed their warm-up, if you'll press play again, I will go over the directions, go over the warm-up. Okay, on your warm-up, I asked you to give a function whose domain was this and whose range was that. So here is an example. Your graph may not look just like this one, but this is an example of a function that could do this. All right, so the domain goes from negative infinity to 2, so negative infinity to 2. And the range is negative 3 here. So from negative infinity to 2, it could look like this. Now, it doesn't have to be this because the range, we could do it slightly different. And then the second one would be where the domain goes from 4 to infinity and the range goes from negative 1 to infinity. Once again, this could be curved. This could curve out and up and out, could go straight, could do a lot of things. And that would give us this part of the function. Now, on number 2, the domain is from negative infinity to positive infinity, and the range is from negative infinity to 4. The zeros are negative 5 and 2. My x-intercepts are negative 5, 0 and 2, 0. My y-intercept is the point 0, 2. This function has an absolute max, and the maximum value of this function is 4. We only have intervals of increase and decrease here. It is increasing from negative infinity to 2, and it is decreasing from negative 2 to infinity. The end behavior, as x approaches negative infinity, y also approaches negative infinity, and as x approaches positive infinity, y approaches negative infinity. And to create a function with even symmetry, we would need to shift it over to the right 2 units. So we remember we do the opposite when it affects the x. So instead of positive 2, we're going to do a negative 2 here. So take a moment, correct any of these that you need to correct, and as soon as everyone has corrected, you can unpause the video and press play again. The next thing we'll do is go over the homework. Okay, on last night's homework, we were reflecting and shifting. Number 1 reflects over the x-axis because the negative is out in front of the function. So this is shifted right 3 units in a reflection over the x-axis. Number 2 is a reflection over the y-axis. So first we're going to reflect it over the y and then shift the whole function up 4 units. Number 3, it was shifted left 2 units, reflected, and then dropped down 3 units. So this is a reflection over the x-axis. This one is a reflection over both the x and the y. So we can reflect it over the x and then reflect it again over the y. Reflect over the y and then again over the x. Or you could have gone the other way. Reflect over the x and then over the y. And we would end up in the same position. So number 1 is the blue one, number 2 is the red one, number 3 is the green one, and number 4 is the purple one. All right, now let's take a look at our other functions. These are the other 4 you were asked to do. So the first thing I'm going to do is draw in the parent graph on these. So the parent graph is y equals x squared. So this is what the parent graph would look like for this particular function. So we're going to take each one of these points, and because of the negative here, we're reflecting it over the x-axis. So this point would flip down to here and then go down 1, 2, 3. Let me switch colors here. So it would flip down and go down 1, 2, 3. It is now here. This point can't flip over it because it's on it, so it just has to go down 3. Flip over, down 3. Flip over, down 3. And so these points are actually off the graph slightly. There we go. And there is the transformation of that function. This second function, there aren't a whole lot of points that fit on this graph. But, whoops, let me switch back to black for the original parent graph. And then these would be down here at negative and positive 8. So they're actually slightly off the graph. Whoops, missed it. Okay. We are to flip them over the x-axis because of the negative here. Because of this negative out in front, we're going to reflect over the x-axis, and this one also shifts down 3. So it's a reflection and a shift of a different function. So reflect it, shift down, reflect to here, shift down 1, 2, 3. Reflect and shift down, reflect, it moves it up here and down 1, 2, 3. And so it took the function, and now it looks like this. Okay, this is the square root function. So I'm going to graph the parent graph just so we can see how it looks. And those are the points that fit on our graph. Now the negative is here, which means the first thing we're going to do is reflect over the y-axis. So this point doesn't go anywhere, and then we go up 2. This point gets reflected over the y, and then up 2. This point gets reflected over the y and then up 2. That is a reflection over the y-axis. This is a reflection back over the x. So we take that parent graph that we just did, the square root function. We're going to shift left 4, reflect, and then up 2. So the first point that's actually on the x-axis won't go anywhere. We'll go up 2. Then we'll go shift the next point left 1, 2, 3, 4, reflect up 2. This point shift 4, reflect up 2. And there's our function. Okay. I have already put these notes on the website, so if you need to go back and print these out later on and look at what I've done here, you certainly may. For today's lesson, we are going to talk about, we're going to add to our reflections vertical stretches and what word do I like to use? Compressions. But since shrinks is also widely accepted, I am going to show it to you just so you'll know what that means. Okay, we've already talked about reflections. This is a review. A negative out in front is a reflection across the x. This point becomes this one because when we reflect over the x-axis, it changes the y to the opposite. Y equals f of negative x is a reflection across the y-axis, and a point xy would become the opposite of x and y. Today, what we're going to add to that is those vertical stretches and compressions. And we talked about this the other day in terms of a rubber band. When we vertically pull or stretch a rubber band, it gets more narrow. And we vertically compress a rubber band, it becomes wider. And that's the same thing that happens when we do a vertical stretch or a compression to any other functions. So this is just the standard form, y equals c times f of x. If this c is less than -1 or greater than 1, it's a stretch. Now another way I could write that is if the absolute value of c is greater than 1. Because we don't care about the sign. The sign tells us reflection. Same thing here. This is really the absolute value of c. between positive and negative 1. That would be a vertical compression. And let's take a look and see how this works. All right, this one we already know. It's a parent graph for our quadratic, but it's been reflected, so all of these are negated. And these are our points. Okay, so that's how our original, and notice how wide it is. That is a normal width for our parabola when it hasn't been multiplied by anything. All this is a reflection over the x-axis. But when we take this and we throw this 2 in here, what it's going to do is take all those squares and double them. So when I square negative 3, I get 9, but when I double it, I get 18. And when I square negative 2, I get 4, but when I double it, I get 8. Negative 1 squared is 1, doubled is 2. 0 is still 0. 1 squared is 1, doubled is 2. 2 squared is 4, doubled is 8. And 3 squared is 9, doubled is 18. So what this does is it takes that parent graph that we've looked at several times, and it stretches it vertically. So see, now we have the point 0, 0, negative 1, 2, and 1, 2. On the parent graph, the parent looks like this. I'm going to draw the parent in here in black, just so we can see the difference. These are the points on the parent graph, the ones in black. Now let's, and I'm going to sketch it real lightly, well, as lightly as the Moby board will let me. And then the one in red are after our vertical stretch. So this would be over 2, up 2, 4, 6, 8. And we should notice that our function became more narrow. This is a vertical stretch by a factor of 2. Okay, and do you see that if I took this y value and doubled it because of the 2, it gives me this one? And if I took this y value and doubled it because of the 2, it gives me this one. Same thing here. Double this y value, get this one. Double this y value, get that one. That is what this vertical stretch is doing. It's doubling the y value, doubling the value of the function. Now let's take a look and see what 1/2 does. When I square negative 3, I get 9. Half of that is 4.5. When I square negative 2, I get 4. Half of that is 2. Half of 1 is 0.5, or 1/2. Half of 0 is still 0. Half of 1 is 0.5. Half of 4 is 2. And half of 9 is 4.5. Okay, so first thing I'm going to do is draw the parent graph in. This is that same parent graph for the parabola that we've looked at several times now. Okay, there's the parent. What happens when I multiply by this 1/2? What does it cause? Well, it makes these points happen. Oops, I didn't go over far enough. There we go. So this causes a, yes I did, should be there, a vertical compression. You should see that it's been pressed down, and when it presses down, it widens out. So this is a vertical compression. By a factor of 1/2. And what that causes is the graph to widen. Now, because of the 1/2, let's check out our y values. That is not your bell. That is just the bell that's occurring while I'm videotaping. Half of 1 is 1/2. Half of 4 is 2. And do you see how that's how we got our y moves? Half of 4 is 2. Half of 1 is 1/2. So we can just take half of the original to get these points. All right, let's see how this works with a different function. Now we have absolute value. And it looks like on this first one, I want to go ahead and get rid of the negative that was out in front. And let's graph this like it was a regular absolute value. So the first thing I'm going to do is draw in a new x-intercept down here. And I'll call that my x-intercept. I just want us to be able to see this parent graph clearly on this one. This is the absolute value that we've graphed several times. And it looks like the V. And we get that from taking the absolute value of these numbers. And so I have changed this problem slightly, so delete the negative. And so this is our parent graph. We're starting off with our parent. So what would multiplying the y values by 3? See our 3? Let's just multiply those y values by 3. What is 0 times 3? It's still 0. Now right here we had a point at 1. But what is 1 times 3? Well, 1 times 3 is 1, 2, 3. Here we had a point at 2, 2. What is 2 times 3? Well, 2 times 3 is 6. Let's do this side. This is the point negative 1, 1. 1 times 3 is 3. This is the point negative 2, 2. 2 times 3 is 6. And here is my new graph. So if we look at this and comparison of the parent graph looks like this. Can you tell it's been vertically stretched? Pulled vertically, and that makes it more narrow. Now let's make sure this actually works. If we took the absolute value of negative 3 and tripled it, we get 9. If we took the absolute value of negative 2 and tripled it, we get 6, 3, 0, 3, 6, 9. The 9s aren't on our graph, but let's see if these points are. Do we have a point at negative 2, 6? Yes. Do we have a point at negative 1, 3? We do. 0, 0, 1, 3, and 2, 6. So just by tripling the y's from our parent graph, that gives us our new transformation here, this vertical stretch. This is a vertical stretch by a factor of 3. Okay, and let's look at the next one. This one's 1/3. So it's going to take that parent graph, all these y values, and multiply them by 1/3. So here's my regular absolute value. It's the V. And once again, I will give you the parent graph. This is not something you have to create. I will give this to you. But you do need to be able to go, okay, 1/3. What's 1/3 of 1? That's 1/3. What's 1/3 of 2? That's 2/3. What's 1/3 of 3? That's 1. And so we might just want to pick the ones we can take 1/3 of easy. And then we can draw. And just do the 1/3 of 3. And this is a vertical compression. You can tell the graph looks like it's been pressed down, flattened out. A vertical compression by a factor of 1/3. All right. Here are some for you to try. I'm going to let you try those in just a second. I want to go over what happens here first, and then at the end you can press pause and I will work some of the you tries and you can check it at the end of the lesson. On this type of problem, when I give you my made-up function, this is the same one we've seen a couple days, and I ask you to do 2 times f of x. Well, we know that f of x means y, so this tells me I'm doubling the y's. Ignore that bell also. If we look at this point, -8, -3, if we double the y, do you see that the point -8, -6 should be on this graph? -8, -6. If we take this point, which is -6, 5, and we double the y, we get negative 6, 10. So this point, negative 6, 10, should be on this graph. If we take this point, which is negative 3, 2, and we double the y, we get negative 3, 4. And if we take this point, negative 2, 2, and we double the y, we get negative 2, 4. So this is the vertically stretched transformation of this function. Oops, forgot to write these two down. So that would be negative 3, 4, and negative 2, 4. Okay, if we were to take half of them, you'd go back up here, take each of these ordered pairs, and do half. So we would get the ordered pairs, negative 8, negative 1.5. Negative 6, positive 2.5, excuse me. Negative 3, 1. Negative 2, 1. And we could plot those points. And so we should be able to tell this one has been vertically compressed. It's been pressed down, vertically compressed. And then the next two add the compressions and the stretch along with a reflection. So all we would have to do on this one is take all of the ordered pairs from number 1 and do the opposite of the x. And all we'd have to do on this one is take all the the numbers here and shift them right 3 and up 1. Okay, I'd like you to take this time to go back and do these U-tries. The U-tries that are on this page. And then go ahead and press pause. And when you've had a chance to work on some of these, then turn the video back on and you'll see me go through the answers of these. Your homework tonight will be, it's defined, your vertical stretches and shrinks homework. And you are just to describe the transformations on 1 through 8. But then, on this bottom section, you're supposed to actually do the graphs without making a table. Okay? All right, so take a moment now, come back to do some of these U-tries. If you finish the U-tries before your peers, you can go ahead and start your homework. And press play when you're ready to check these out. Okay, number 1 is a vertical stretch by a factor of 3. And I'm just going to write by 3 here because I'm running out of room. Okay, the regular one looks like this. 0, 0, 1, 1, 4, 2, and 9, 3. There we go. So if we vertically stretch it by a factor of 3, all these y's get multiplied by 3. So up 3. Okay, so this was 2, now it's 6. This was 3, now it's 9. So it's been vertically stretched by a factor of 3. This is two things. It is a reflection over the x and a vertical compression by a factor of 1/2. So here is the original function. Once again, same function. And we're going to flip it and multiply our y's by 1/2. So half of 1 is a half. Very close. Half of 2 is 4, and half of 3 is 1.5. It's hard to even see the curve, but it looks like that. Okay, let's take a look at 3 and 4. Okay, 3 is the cubic function, and it looks like this. Here is your parent graph. And so it goes up and swoosh right through. Okay, but this time we're going to multiply by -1/3, so it's going to flip it and make it even closer. So this point gets flipped over here and it's multiplied by 1/3. This point gets flipped down here and multiplied by 1/3. The 8 gets flipped down here and multiplied by 1/3. 1/3 of 8 would be 2 2/3. So it looks like this. And this one would get flipped up here and look like that. So it's got nice and fat. It's been vertically compressed and reflected. This one has been vertically stretched, so it's gotten even skinnier. So it's the same parent graph for this one, but that 1 gets multiplied by 2. That 8 gets multiplied by 2, so it would be 16. Does not even fit on the graph. The -1 gets multiplied by 2. The -8 right here gets multiplied by 2. Does not fit. So this has really been vertically stretched by a factor of 2. This is a reflection over the x and a vertical compression by a factor of 1/3. Okay, let's look at the last two. This was y's are doubled and shifted up 1. So parent graph is here. This is this parent, and you should just be able to copy this out of your packet. I'm not asking you to memorize the parents. Those are the points on the parent graph. So we're going to double and shift. Double 0 is still 0, shift up 1. Double 1 is 2, shift up 1. Double 4 is 8, shift up 1. And there we go. So this is a vertical stretch by a factor of 2 and shift up 1. This is a horizontal shift. Right 3 units. A reflection over the x. And it is also a vertical compression by a factor of 1/2. So same parent graph as over here. It's still the parabola. But we're going to shift it to the right 3, so that 0 will move over here. When I multiply 0 by 1/2, it's still 0. Okay, this point here gets flipped over and multiplied by 1/2. This point here gets flipped over, shifted right 3, and multiplied by 1/2. This point here gets flipped over, shift over 3, and multiplied by 1/2. So now it's at 2. And this one gets flipped over, shift over 3, and multiplied by 1/2. So it's right here at 2. And it looks like that. Okay, you may take the rest of class to work on your homework.